Okay, hey folks, let's pick up right where we left off. And now we're going to start getting more into calculations with our metals. And mostly what I'm interested in you to be able to do here are calculating physical properties of various solids, such as their density or even their unit cell dimensions. Okay, so let's first talk about each of our unit cells that you're responsible for in this class, which is our simple cubic, our body-centered cubic, and our face-centered cubic. Okay, and this A right here we can see is what we call our lattice constant. Okay, and that lattice constant is simply the length of our cube. Okay, so here you can see this letter A is signifying the length of that cube. And we could use any letter we want for this. So this could be A, B, X, L, W, whatever. So we just want to get used to recognizing that we might have a different letter for this thing. There's no standard letter for unit cell dimension. But we want to recognize when we see this lattice constant or sometimes unit cell dimension, this is the quantity that we're talking about. Okay. The other thing we need to be able to work out is how many atoms are in each unit cell via this question. And that might seem like a trick question, right? Like when you count this up, for example, simple cubic, you might say 1, 2, 3, 4, 5, 6, 7, 8. There's 8 atoms. But that's not true because each unit cell shares a dimension with the next unit cell over, okay? And so this picture is a good guide right here. And for example, if you notice here, a corner atom actually counts as 1/8 of an atom. And I also want to make sure we're clear on this. We're not cutting atoms in half. We do not have the ability to do that, to slice an atom in half perfectly like this. This is just for physical representation because we recognize if I were to draw another unit cell over here, this 1/8 of an atom would be shared by 8 other unit cells to make it a full atom. Okay, so what that means is if each of these corner atoms in our unit cell is 1/8, okay, so I'll point to that one right there, and we have 1, 2, 3, 4, 5, 6, 7, 8, then that means we have, I'm going to write 1 full atom per unit cell. And as it turns out, we can relate the density of our solid from this very simple concept, okay? So our bulk macroscopically observed density is based on this picture, which is really cool. Okay, so what if we looked at BCC, the body-centered cubic? Well, we recognize that there's 1/8 of an atom on all the corners, and there's 8 of them, so that's 1. And in the center, there's 1 full atom in the center. So that means BCC has 2, all right, full atoms per unit cell, okay? And then now finally, this FCC looks a little complicated, but if we now rely on this diagram right here, and hopefully we can recognize now this is a picture of an FCC, this specifically unit cell here is face-centered cubic. Each atom that's on a face counts as half an atom. And it might be difficult to see this, but if we count carefully, we recognize that there's 6 sides to a cube, okay? 1, 2, 3, 4, 5, 6. And there's a half of an atom on each of those sides. So that gives me 6 times 1/2 is 3, plus there's 1/8 of an atom on each corner, and there's 8 corners. So that means our FCC is 4 full atoms per unit cell. And what we would actually expect to see for a material, if let's say the unit cell is the same, so about the same dimension. But then we start cramming more of these atoms in these unit cells, 1, 2, 4, we would expect to see the density go up by a factor of 2 each time. So in fact, the density of a material is exactly related to how many atoms are packed into its unit cell. Okay, and we'll see that in a calculation coming soon. So I also want to talk about how we can relate the radius of an atom to its lattice constant. And here, once again, this picture was using L, and I know my last picture was using A. There is no like uniform letter for our lattice constant, so we just recognize lattice constant is the length of our cube. Okay, so let's start with the simple cubic. So this is our simple cubic. We recognize that that's 1 full atom per unit cell. And now if we wanted to relate the radius of the atom to its lattice constant, we can just simply do some geometry right here. Okay, so I can see that I've got 1 radius right there. I know that that's like 1/8 of an atom, right? But this length goes from half of this atom to half of the other atom. So that's 2 radii, right? There's 1 R and then there's another R, so that makes it 2. Okay, so we could say L equals 2R, or we could say R equals L divided by 2. And we gain useful information from that, being able to calculate the size of atoms, knowing the unit cell dimension or vice versa. All right. So now let's look at our BCC. So that's this picture right here, our body-centered cubic. And I'm not going to hold you responsible for this geometry, but if we were to go for a cube from this corner all the way to this back corner, so we're drawing a line and it actually goes diagonally through the center of the cube. Geometry tells us that length is L times √3. Okay, and now if we start to count how many radii this goes through, we might have to stare at this for a minute to see how this works. But we know that it's in this corner atom, it's going to go through 1 radius. Okay, now it's going through a full atom in the center, so that's 2 radii. And then it goes through a 4th and final radii to get to this corner. So that means L times √3 equals 4R. Okay, so we could relate that to radius, or we could keep the equation just as is. So I'll write that we could say the radius of the atom is now L times √3 divided by 4. Okay, and I'm not going to make you memorize these equations, but if we were to have some kind of a picture like this, I do want you to be able to comfortable with counting, these number of radii to deduce physical information about our unit cell. Okay, so that means you'll either be given the equation or you'll be given this picture. All right. So, and now finally, our FCC, our face-centered cubic. So if I go from this corner to this corner, so on the same face, geometry tells us that's L times √2. So L times √2 equals, and then now hopefully you can see that that's going through 4 radii. So 1, 2, 3, 4. So that equals 4R. And once again, I could say, R equals L √2 divided by 4. So this gives me a means of calculating the size of my atom, assuming that I have knowledge of its unit cell. And I gain knowledge of its unit cell by knowing its density, which is pretty cool. So we can actually use that what I call bulk scale information, such as the density of a chunk of solid, and we could back calculate that all the way down to the size of the atom. And we're going to do that next in a part B video.